Today we're going to start chapter 7. Chapter 7 is about decimals. So today's an introduction to specifically finite decimals, and we'll talk more about what that means in a moment. The word decimal comes from the Latin word meaning 10, that DEC at the beginning. So we see that prefix in lots of things: decade, 10 years, decagon, 10-sided shapes, things like that. So that's where it's coming from. The language that we use and ascribed to decimals has to do with our place value system. So when we look at this, we have a couple of place values, and I'm going to put a dot, and we're going to go 6 lines to the side. So the first place value before our decimal place is the tens place. And then we have either the ones or the units place, depending on the resources you're looking at. And there's our decimal. And then everything else after that's going to have that THS on the end. So this is the tenths place. So I'm going to be overemphasizing that ending sound to be really clear today. At least that's going to be my goal, so that we can hear it really well. This is the hundredths place. What's next? Yes, thousandths. Do you know what comes after thousandths? Yeah, it is 10,000. So I lost my S. I should keep that S with there. Yeah, it's 10 thousandths. What's after 10 thousandths? 100 thousandths. And notice they're hyphenated between the 100 and the thousandths here. And then what's after 100 thousandths? Any guesses? It is. It's millionths. And it doesn't stop. We just are not going to write things out forever, so we're going to stop. What would come after millionths? 10 millionths, and then 100 millionths, and then billions. Yeah. So it keeps going indefinitely. Ours are not going to get any bigger. I think there may be one example that puts you in the 10 millionths, maybe, but that's going to be it. It's not going to get any further out than that. What we are going to be doing, however, is learning to properly say this number. Because if I were to ask you to say it right now, you would probably say something like 32.4236, right? Yeah, that's what we say. It actually has a proper way to be said. This isn't exactly the best example for my description as to why, but if you write checks, I think that's growing to be a lost art. But when you write a check, you actually have to write the words of your dollar amount out. Obviously, it doesn't go out to lots of decimal places, but anything before the decimal has to be written out. So I actually just wrote a check for a large sum of money that I'm sending to Arizona because it's being taken in cash, like actual hard cash, to Ethiopia in a couple of weeks. And it's a $13,000 check. Probably the biggest check I've ever written. That's a big amount of money. And it wasn't just 13,000, it was 13,415, and I had to write out all those words for it, right? Well, the same thing's true for this. It has a language form, properly said, and we're going to say it. So the number beforehand we do pretty good with. This number is 32. And it is hyphenated. When we get to the decimal point, we say the word and. I remember being in second grade specifically. I had a teacher who was super critical, specifically of me. She probably was of other kids too. Just you don't think about that when you're in second grade. And I like to put the word and in the middle of my numbers. So I'd say something like 450. And she'd get all upset. But I never knew why, right? I didn't understand why it mattered then. Well, it matters because and actually represents a decimal point, okay? So it's not 450, it's 450. Because the and would be coming after that number. So we've got our and there. This number right here, we're going to write it out and ignore everything right now except for the fact that we've got 4236. So if I were to think about this corresponding number, how would I say 4236 and ignore the fact that I'm in the decimals locations? And that's what we write next. Okay, so we're going to write down 4,000. $236. And then at the very end, we identify the place value that our 6 is falling in. So the 6 is falling 4 decimal places to the right. So what is the language corresponding to that location? 10 thousandths. So we write that after this. 10 thousandths. So this number in words correctly, can you guys see it? Is it big enough? Okay. Is 32 and 4,236 10,000ths.
So glad there's not more than 2 decimal places for money.
Yeah, it would be harder, except when you're doing gas. So they like to put the third decimal point on there for some reason. All right, so we've gone from a number to the words, and we're going to go from the words back to the number. So here is our words for this one. It's 536 and 67 thousandths. So my suggestion is to first identify if there's an and, because then you'll know where you're working on the far, on the left side or the right side of the decimal point. And there is. So we've got an and right here. So I have this number on the left, and I have this amount of the number on the right. Okay, so what digits am I going to write down from left to right first?
536.
536, and then I have a decimal point, right? Okay, now this says 76. That's 76. But this tells me where I have to end my value. How many places am I ending to the right of the decimal? 3. Yeah, it says thousands, so I need 3. 76 is just a 2-digit number, but it has to end here. So you put a 0 there. You do. It is a placeholder. Okay, everybody good? So you're going to do a few problems. You're not going to do a ton of ones, but a few problems where you're working back and forth with language and sort of number form conversions, okay? Also, we're going to be thinking about how our number system corresponds back to fractions. So we're not working in fractions, but there obviously is a correlation back to fractions, and we're going to make that connection. So in our place systems, we have the hundredths place, we have the tens place, and we have the ones place. There's a decimal, and then I'm going to do the equal numbers of them on the right, just three decimal places on the right. Now, we called this place in words the tenths place, right? That's what we called it. And the reason we do is because the fraction represents the fraction 1/10. Right? Think about a dime. It's 1/10 of a dollar. That's what a dime really is. It's 1/10 of a dollar. Okay? What's the next value? Yeah, 1 over 100, right? It's like our penny, yeah? Yep. And the next one would be 1 over 1,000. And this continues on indefinitely, right? 1 over powers of 10. Now, your book likes to do answers in the back of the book with negative exponents. And I normally don't just disagree with the book. I just go with what they're going with. But I don't want you to do that. And the reason that I don't is because I think that it loses the intuitiveness of its connection to fractions and what the purpose and the meaning are when we do that. They are powers of 10, right? This really is 10 squared. And this is 10 to the 1. And this is 10 to the 0. And 10 to the... They are these values. There's no doubt about it. But I don't think that you're getting a very good picture of what they're representing if you're using these exponents as you are if you're using the place value written in a whole number, like 100, or a fractional 1 over 100 point of view. So as you're looking in the back, just make sure that it matches, but I don't want you to use negative exponents, okay? So we're going to write a number now in expanded form. This is called expanded form, and so we are going to take each of our values, and instead of just writing them as single digits all merged together, we're going to write them as the value they are. For example, this is 1/100. It's 0 tens, and it's 3 ones. So imagine you're going to the bank. You're the teller, right? You're counting back the volumes of money that somebody's asked you. These are what you're giving them, right? That's the actual bill breakdown that you would give. Now I have a couple more. I have a 0 here, and it's in the tenths place, so this is 1 over 10. And then I have a 3, and it's in the hundreds place, so 1 over 100. Parentheses around things, dots between things. It doesn't matter to me what notation you use. I really would prefer you not use an X, because there will be problems occasionally where we'll come across an X being used as a variable. So please don't do that. But otherwise, this will work just fine. Any questions on that? Really? So we talk about it in number theory as well. I don't know if you've taken number theory yet, but yeah, it comes up in there. One of the things that this does, and I should have brought this happens every time I get to 7.1 because I'm so eager to give back tests that I never think to bring them. There's a manipulatives. Oh, I have it because all my manipulatives are here. Just a sec. Okay, so good news, I do have the manipulatives. This actually is talking about a decimal square grid. So this is what a decimal square grid looks like. Okay, it's a 10 by 10. I'll pass these around to you guys. Whatever. So you can actually see a little bit closer up. Okay, so these decimal square grid is 10 units long and 10 units wide. Everybody good with that? So if I use this whole piece to represent a whole number, then each of the strips, which would look like these, are 1/10 of the whole picture, right? And each of the little blocks themselves, I'm throwing them, like this, is 1/100th of the whole picture, okay? So we can count like objects, right? So I can count this one, this is 1 hole, this is 2 holes, this is 2 holes. And I can count this is 1 and this is 1/10, but this is not 2 because they're not the same size, which looks a lot like something on your test that you just took from me, right? This is the problem. This is not 2. So the size and the shape tell us how we can combine things together. So in our decimal square grid, I'll pick those up at the end. You're going to be drawing, to the best of your ability, a image of what I just gave you. You're just going to trace it. You might be able to. Oh, I'm sorry. Okay. And my grid's not going to be any better than yours because my tools are really not any better than yours on this one. So we're going to make 10 columns. They're going to be approximately equal, and we're going to just hand wave and say that they are if they're really not. Because they certainly are not. This looks awful. Oh my goodness. I got to try again. I can do a square. I can't do my line straight down.
That was not perfect. I was like, what?
Okay. So mine's not any better than yours. Some of you are very pleased with what you're drawing, I can tell. It's wonderful. I'm so excited for you. Could have been a lot worse. That's definitely a good thing to go with. All right, cool. So this is a decimal square grid, right? It's a 10 by 10. There's 100 little bitty squares, and it works really well when we're representing things that have 2 digits, like our money would work for this. Of course, we have actual coins that would represent the idea similarly. But what we're going to do with example 4, and at this point I do get to cheat because I can copy paste. Yeah, sorry about that. No copy paste on your piece of paper. I bet Abby's over there copying and pasting, aren't you?
Yes.
All right, so we have our decimal square grid, redrawn-ish, and it says that we're going to shade in, or we're going to draw the decimal square grid for the number 0.24, right, 24 hundredths.
Yes.
So if this whole grid is 100, what do you think we're going to be shading in? 24. And while technically you can shade in any 24 boxes and it would represent the right value, if you do shade in random 24 of them, I'm not going to be very happy, and my grader will probably be even less amused. Because it's a lot easier, right, for us all to grade if you just shade in 2 rows, that's 20, and then 4 more, because I can count them very quickly and see that you've shaded in 24. It doesn't matter whether they're shaded vertically, horizontally, it doesn't make any difference. This is 24 of my 100 little boxes. Okay. So there is a connection as well between fractions and what we're looking at right now, which are called finite decimals. So a rational number, a over b, right, stuff from chapter 6, in simplest form can be written as a terminating decimal. That's a finite decimal, it ends. If and only if the prime factorization of the denominator contains only 2's and 5's. And it doesn't mean it has to have 2's and 5's. It just means those are the only options. So it could only have 2's, it could only have 5, or it could have some of both. So when we're trying to decide if a number actually represents a terminating decimal, this is what we're doing. We do want to make sure that we're connecting the fact that this has to be in simplest form. Okay? So I start with a fraction. We're going to do a couple of examples here. And I want to make sure first that it's in simplest form. And once it's in simplest form, I factor the denominator. And then I can make a decision about whether or not it's going to represent a terminating decimal or not. So this says mentally determine. I don't like it when our book gives you instructions to do things mentally, because I still need you to write some of it down. Otherwise, I won't know what you did mentally. But I should be able to look at it and think, you could do that in your head mentally, right? So if you do something that's going to take like 15 steps, that's not mental math. Right? It's got to look like something that could be done in your head, right? They have to go together. So thinking about this one as we're mentally determining it, it's wanting us to use this idea over here. Simplest form, factor the denominator. So 9 and 24. Is 9 over 24 in simplest form? No. What can I reduce them both by?
30.
Yep, I can divide both of them by 3 to give me 3/8. Yeah? Okay. And then I take the number 8 and I factor it. How does 8 factor? Actually, good. 4 and 2, and 4 becomes 2 and 2. So the number 8 is actually 2 times 2 times 2. Yep. Okay. So looking over here at my definition then, does that denominator factor into only 2's and or 5's?
Yes.
Yes. I don't need both. I just can't have anything else besides 2's and 5's, right? So no 3's, no 7's, no 11's, none of that. 2's, 5's, nothing else. And it does. It just has 2's. So the answer is that yes, this represents a terminating decimal. And actually that's not the answer we wish it were, because it means then we have to do more work. Because it says if it's a terminating decimal, write it in that form. So we're actually then going to write it in that form. Now, while you can take 9 and divide it by 24, it'd be a whole lot easier to do 3 divided by 8. So I'd use the reduced fraction if I were you, and I do expect to see the division. I know. Just like you would expect to see out of your kids when they were working with fractions and decimals and everything for the first go-rounds. Eventually they used these calculators too, I know. But initially, this is where you start. So we're going to do the division. So how many times does 8 go into 30? Well, 8 goes into 3 0 times. I should have written that one down. How many times does the 8 now go into 30? 3. Sorry, you were just answering the question that I failed to ask. 3 times 8 is 24. And subtract, we get 6. We bring down another 0. 8 goes into 60. 7 times. I know those multiplication facts. It's been a little bit. 7 times 8 is 56. And we subtract to get 4. We bring down a 0. They will end, right? That's the whole thing we know it's going to happen. 8 goes into 40. 5 times. And what is 5 times 8? 40. Once we get to a remainder of 0, this is my stopping spot. And the decimal right here that I got is 375 thousandths. Okay, so should you check on your calculator to make sure you did it right?
Sure.
I think you probably should. It's right. But you've got that as a resource, so definitely check your work. But I want to see the division steps written out, okay? Okay, any questions on that? Okay, how about B? Is 10 over 24 in simplest form? No. What do we need to divide by? 2 on top and bottom. So 10 divided by 2 is?
5.
And 24 divided by 2? 12. Okay, 12 factors into?
6 and 2.
Okay, 6 and 2. Or 4 and 3, just pick one, yeah. And then 6 is?
3 and 2.
3 and 2. So 12 is 2 times 2 times 3. Is it a terminating decimal? No. And in fact, if you try your calculator, like if you use your calculator to try, at some point you're going to get a repeating decimal in this. Those are the only two options, okay? You're either going to get a terminating decimal or a repeating decimal. So your calculator can also help you to know what the answer is in terms of the yeses or the nos here. But again, your work has to support that you understand the why. The why is because the denominator has 3 in it when it's simplified. All right, our next thing we're going to look at is ordering decimals. So our question is wanting us to line things up here in a moment in order from like least to greatest or greatest to least, put things in order. And so we're going to line up the numbers by place value. My recommendation is to write them on top of each other because it's easier to see them, I think, vertically than horizontally and make a comparison. We're going to read the numbers from left to right and find the first difference, the first place where they are different. And then the third thing is to compare the different digits. So we have 4 numbers given to us here. And what I'm going to do is I'm going to leave the first one where it is. I'm going to write the other 3 underneath it. Okay? So we have 13. I've got my decimal point and then 492. 13, 49183, 13, 49199. If it bothers you that they're not all the same length, you can put zeros on the end of things to make them the same length. Right? So there's a 0 right here, here, and here, if you want to see them the same length. That's sort of, I'll try and separate it from the rest of my numbers. If you don't care to have the zeros, then don't put them in. It doesn't bother me either way. The directions do say that we're going to go from least to greatest. So we want to look at these numbers and identify the first one as the smallest, the last one is the greatest, and we're going to work from left to right. So the first column all matches, as does the units column, right, the ones digit. The tenths digit matches, and so does the hundredths. So all of those are the same. Feel free to use colors to highlight things, use a ruler to cover things up as you go, whatever it helps you to get them in the line correctly. But the first number that's actually different is this middle number here, the second one. It's the biggest because it's a 2 and the others are 1s, right? So if you're thinking like in order from smallest to greatest, this is the greatest one, so I'm going to call it number 4 because I'm supposed to be putting them in order from smallest to greatest. This will be the greatest one, number 4. So we're going to ignore line 2 now because I've already decided where he falls in the mix. So now I'm only considering line 3. Okay, so line 3 has the 9089 on it. Okay, the 0 doesn't matter. I'm rather ignored this at this point, right? It's no longer under consideration. I've got a 9 on the top one, an 8 on the third one, and a 9 on the bottom one. So the 8 is different. What can you tell me about this number that's in the 8s?
The smallest.
This one's the smallest, so it's going to be the first one on my list when I write them in order. And now I'm going to ignore it. And then my last digits for the first listed and the last listed are a 0 and a 9. So what does that tell you? Where do they come between 1 and 4? Which one's 2 and which one's 3?
The bottom's 3rd.
The bottom one is 3rd because the 9 is the larger. And the top one is the second one because it's the smaller of the 0 and the 9. Okay, are we good? Right? So we're going to list them now from smallest to largest. The first one was this one. This one is 2. This one is 3. And this one is 4. But we're going to write them out. So this is 13.49183. You can put a comma if you wish. I'm going to just use the symbols less than to keep in my mind that I am putting them in the order I was requested to do. The second one is 13.4919. The third one is 13.49199. And then the last one is the 13.492. Okay, any questions on that? Okay. One of the ways where we see decimals used regularly is in the meaning of the word tithe. Do you know what the meaning of the word tithe is, and how is it related to decimals? Abby.
You're giving a certain percent of something, normally it's money.
Mm-hmm.
And so if you're like tithing 10%, that means you're tithing 0.10.
Okay.
What you have.
So I'm going to take what you said, and I'm going to make one little tweak to it. So the word tithe isn't just some percent, it's actually always 10%. So the tithe means 1/10, which is the decimal point, or the fraction like this, or the decimal point like this that you mentioned, 1/10 of something. And you're right, in our practice of our faith, this is typically money. In Judaism, they would tithe 1/10 of all kinds of stuff. There's a passage in a couple of different Gospels where Jesus accuses them of tithing 1/10 of their spices. I think it says dill, cumin, and something else. 3 spices, random spices listed in the New Testament. Can you imagine going home and partitioning out 1/10 of your cinnamon from the cabinet and giving it to the church? Like, I just can't imagine. So it doesn't have to be money, but our faith practices it with our increase, right? Our numerical increase, our money. So in practice,
What is that middle at right after the 1/10? Oh, 0.1.
it's 0.1, sorry. Yeah, it has nothing around it to give us a reference point. In practice, we take our income say you made $100 doing something, and 10% or 1/10 or 0.1, right? All mean the same thing. Of this is our tithe. And what is that value? What is 10% or 1/10 of 100? $10, right? $10. Any questions? Yep, Abby.
This is just like about tithing. So why does tithe mean 10% if some people tithe like 20% or 5%?
The definition of the word tithe is 1/10.
Okay.
Yes. So people use it incorrectly all the time and say, I'm going to tithe 5%. Tithe actually has the connotation also to your local church, like where you locally practice. So truly and technically, biblically speaking, you can't just decide who you're going to give your tithe to. Like we had when we were raising money for our very first adoption for our son, I had a friend that says, I think you should tithe to yourself for bringing your son home. Like, well, we can certainly keep our money or not, but that's still not a tithe, right? Like, that doesn't make it a tithe. Tithe is money that's given to your local church. So, yeah, it's the definition, and people use it wrong.
Okay.
Mm-hmm. Yeah. Any other questions?
Is that a pet peeve?
No, not so much, but I see it used a lot because, I mean, my husband's in the ministry, so we see people say things like that all the time. Yeah. You'll see people, I don't know if you guys are familiar with Dave Ramsey, but people will talk to Dave Ramsey. He's a financial advisor about the same sort of thing. They're like, well, can't I just give a tithe of 5%? Well, you can give 5%, but that's not a tithe. So, yeah.
So like if sometimes the Bible's just like, give what you have, so what if 5% is all they have, it's not a tithe anymore, it's just given what.
Yeah, so that's a different command, and it's usually meaning something that you're doing above and beyond. That's usually where it falls, yeah. And we see places throughout the Old and New Testament both where God makes different accommodations for different income levels, if you will, or whatever. Like reading the Old Testament right now, and there's lots of the Levitical practices where they're supposed to bring a lamb. But if they don't have enough money for a lamb, he allows them to bring a dove instead, right? There's accommodations. And those accommodations actually already fit in with our 10%, because 10% of my salary and 10% of your salary are not the same thing. But they're still 10% of what we have, right? What we've got coming in.